Hi, I'm Jonathan Aldrich, and let's talk about program semantics. First, we'll talk about semantics and abstract syntax trees. While syntax describes the form of a program syntactically, semantics describes what the program means. Now, the line between these two can be a little bit fuzzy, but in practice, syntax specifications are limited by the expressiveness of context-free grammars. And so semantics tends to be everything that goes beyond this. Semantics typically has two parts. First of all, how do we compute the program's output from its input? How does the program actually run? And then also, we use semantics to enforce rules such as type consistency. Some aspects of semantics may be left undefined by a language definition. In those cases, the implementation can choose what to do. And sometimes giving the implementation more choices allows the code to run more efficiently. This is often the case for nonsensical operations. So dereferencing a null pointer is undefined semantics in C, and it's up to the programmer to make sure that you don't do that. On the other hand, undefined behavior in a compiler can be undesirable because the program can do anything at all at that point. And so safe languages try to either avoid undefined behavior, which Java works pretty hard to do, or confine that undefined behavior to designated blocks of code, which may be identified by a keyword such as unsafe in the language Rust. When we talk about semantics, we often distinguish between dynamic semantics and static semantics. Dynamic semantics describe the computations done at runtime, as well as any checks that are done at runtime. In the case of an interpreter, dynamic semantics could be the entire semantics of the language. On the other hand, for static semantics, we have language rules that are enforced at compile time. For example, checking for unbound identifiers, or for checking that operations are passed the right types. In most languages, true plus 5 is not a valid addition expression because what number is true? Who knows, right? So static semantics are typically checked in the semantic analysis phase of a compiler. Now, looking at these two definitions, we observe that most languages do at least some rule checking at runtime. For example, commonly checked rules at runtime might include checked typecasts, null pointer, or array out of bounds errors. On the other hand, the more rules that we can check at compile time, we can gain some advantages in terms of catching the errors early and telling the programmer about them, even before we run the code, or even generating more efficient code because we can eliminate those runtime checks. A semantic analyzer is in charge of enforcing the static semantics of the language. It's also in charge of annotating the program with information that will be used by later stages of the compiler, such as type information. The analyzer is sound if the conclusion it reaches always agree with what will happen when the program runs. For example, if we type check a variable and we know the variable will always hold a certain type, that will be sound if at runtime the variable always holds the type that the semantic analyzer predicts. Similarly, a sophisticated semantic analyzer will be able to check that an array index will never be out of bounds. That's not true of many common languages, but it is true with languages that have additional specifications that can talk about array bounds. Sometimes an analyzer will be uncertain of a required property. For example, as I said, it's pretty rare for semantic analyzers to be able to predict if an array index is out of bounds. And so then we'll insert dynamic checks to verify that the property is true at runtime. And it becomes part of the dynamic semantics of the language in that case. Tools outside the compiler can also check additional properties. For example, linters, or more generally static analyzers, might check style rules or alert the programmer to likely errors. Now, when we analyze the program, we might try to analyze it in terms of a parse tree, but this can be quite awkward because parse trees have a lot of low-level semantic details. In the grammar that we showed for parsing expressions, for example, we have a lot of distinctions between factors and terms and expressions, which are really only useful in parsing. That's generally true of things like precedence, associativity, parentheses. These are really only used to group expressions together and define the order of operations. But once we figure that out in the parser, we don't really need to capture that in the representation of the program anymore. We'd much prefer a more abstract view when we do semantic analysis. So we can take this concrete parse tree and turn it into a more abstract tree form, which we call an abstract syntax tree. Looking at this expression language as an example, we will omit the distinctions between expressions, terms, and factors, and simply have things like integer literals and binary operators. And the binary operator will directly keep track of whether it's a plus or a minus or a times. And then we'll just have, in this case, we have int literals and number literals directly below the binary operator instead of having multiple layers in between. Much simpler to understand and specify. We can use something called an abstract grammar to specify the structure of an abstract syntax tree. For the calculator expression language, an abstract grammar may leave out some details. It doesn't have precedence in associativity. It leaves out syntactic issues such as parentheses. They've gone away by the time we analyze the semantics of the language. And so we have expression forms that are simply variables, integer literals, real literals, float and truncate expressions, and binary operators. Similarly, for operators, we just have plus, minus, times, and divided by. We don't have to divide it into addition operators and multiplication operators. Now, if we were to use this grammar for parsing, it would actually be ambiguous, right? Because at least if we look at the way these constructs are typically represented in source code, it would be ambiguous. But that doesn't actually matter because we've already used an unambiguous grammar to parse the expressions, and so now we just represent the expression as a structure in the compiler runtime. These abstract grammars correspond to data type definitions that you can use in a programming language. Here I'm using some pseudocode that assumes a data type construct that has multiple different cases. In this case, an expression might have cases for variables, integer literals, real literals, and so on. In an object-oriented language, we might have an abstract class for expressions and then concrete subclasses to represent all the different cases of expressions. For operators, we might have an enumeration type to represent the different cases, since operators don't have substructure. Let's check our understanding. For a language with which you are familiar, name one check that's done in the dynamic semantics and one check done in the static semantics. For this question, answers may vary. One answer is that in Java, null pointer exceptions are checked in the dynamic semantics, while checking that operations are applied to the correct types is done in the static semantics.